Hello everybody, this is Mr. Arocena, and on today's video we're going to be talking about how you can predict the direction of a redox reaction. Alright, so in order to do this, it first requires us to look at the final table in our Chem12 data booklet. So this is known as the Standard Reduction Potentials table. And it's arranged very similarly to the table of acids. So I'll pull it up right now. Okay, so here's the standard reduction potential of half cells table, and as you can see, it's kind of similar to how the table of acids and bases is aligned. You have a bunch of reactions, and they're shown as both going forward and reverse. And at the moment, it probably doesn't look like it means anything, but we'll get to that as to how we can read this table. Alright, so here is a sample of the table, and we'll discuss kind of what it means. Okay, so first thing, all of the forward reactions on this table are reduction reactions. Okay, and all of the reverse reactions are all oxidation reactions. So if I take this as an example, the forward reaction would look like this: F2 plus 2 electrons will produce 2F minus, like that. So this is a reduction reaction, because as you can see, the F2 is gaining electrons, so it's a reduction. Okay. Now the reverse reaction will look like this: 2F minus going to F2 plus 2 electrons. This is an oxidation reaction, because it is losing electrons. So in a way, you can show that if the electrons are on the reactant side of the reaction, then it's a reduction reaction. If the electrons are on the product side, it's an oxidation reaction. Because if you remember our acronym, Leo the line says GER. Loss of electrons is oxidation. So oxidation is the reverse reaction on the table, and gain of electrons is a reduction. Alright, so here's the table again. Now, everything on the left side are oxidizing agents. So that's these substances here. So oxidizing agents are the things getting reduced, because they're the ones gaining the electrons. So like F2 would be an oxidizing agent. S2O82 minus is an oxidizing agent. H2O2 is an oxidizing agent. MnO4 is an oxidizing agent. Gold ions 3 plus is an oxidizing agent. Okay. The reducing agents are the things in the middle. So this would be something like, so if you see F minus is a reducing agent, because the reaction goes that way, so it gets oxidized. SO4 2 minus is a reducing agent because it's oxidized. In this case, H2O is a reducing agent because it is getting oxidized in the reverse reaction. Okay. And the final column is what's known as the electric potential. At the moment, this won't mean much, but we will use the electric potential quite a bit later on this unit. And basically, this is just how much voltage this reaction either produces or how much voltage this reaction requires. Now, as you go up on the table, there's a couple of trends you should notice. The stronger oxidizing agents are on the upper left of the table, so as you go up, you get stronger oxidizing agents. And as you go down, you get stronger reducing agents. So the strong reducing agents are in the upper left. The strong oxidizing agents in the upper left. Strong reducing agents are on the bottom right. Right. Now the electric potential, so the electric potential that is written down in the electric potential column, those are the electric potentials for the forward reactions. So they're the electric potentials for the reductions. The oxidations will have the exact same electric potential, only that they are negative. So for example, if you have a reduction reaction of plus 2.87 volts, the oxidation will have a electric potential of minus 2.87 volts. And again, we'll get into what those numbers actually mean later on. But for now, it's just basically a measure of how much electricity or how much energy the reaction needs, or how much energy the reaction gives up. Alright, now in redox reactions, there are sort of three scenarios that can exist based on what kind of reducing agents and oxidizing agents you have. The first, we'll discuss all three. So the first is that both reactions are found on the left side of the table. Basically, they're both oxidizing agents. The second one is where both reactants are on the right side of the table, so they're basically all reducing agents. And the last one is where you have one reactant on the left side and one reactant on the right side. Now, if both reactants are on the left side of the table, this means that both reactants are basically oxidizing agents, so they want to get reduced. Okay, so here's an example. Chlorine gas and bromine gas. Both elements want to be reduced according to the table, so they're both oxidizing agents. So we'll that these are oxidizing agents. And both of them are oxidizing agents. They both want to get reduced. Like, you won't find Cl2, so Cl2 does not appear on the reducing agent side. You'll find Cl- in some places, like Cl- will show up on the right side of the table, but Cl2 does not. Same thing with Br2, you'll only find Br2 on one side of the table. Now, since neither reaction, or neither element, is willing to get oxidized, then no reaction will occur. So like Cl2 already has, Cl2 does not want to give up any electrons, so it won't undergo an oxidation. Same thing with Br2. So in this case, since both reactants are oxidizing agents, no redox reaction will occur. Now you can probably guess what will happen if both reactants are on the right side of the table. So for example, here we'll take iron and copper, and I should make note that these should be solid iron and copper. So iron solid and copper solid. Both of these elements want to be oxidized, meaning they want to lose their electrons. So if you look at the table, you will find the following reactions. In your table, it'll actually be reversed. In your table, it'll be the Fe2 plus 2 electrons going to iron. We're going to look at the reverse reaction, where we get solid iron will want to become iron ion plus 2 electrons. And then the copper will want to become a copper ion plus 1 electron. Neither element really wants to gain electrons, so because neither element wants to get reduced, then no redox reaction will occur. Both of these reactants want to give up their electrons, and neither one is willing to gain electrons. So nothing happens. If they're both reducing agents, nothing happens. So kind of similar to how both are oxidizing agents, nothing will happen. Now, what if you find something that is on the left and something that's on the right? Okay, or one oxidizing agent and one reducing agent. And this is where the table will come in handy. Two cases exist for this particular pairing. Case 1 is when you have the oxidizing agent higher on the table than the reducing agent. So you have a very strong oxidizing agent paired up with a strong reducing agent. So this would be like strong oxidizing agent and strong reducing agent. And case 2 is where you have the reducing agent higher up on the table than the oxidizing agent. So this would be something like you have a weak reducing agent and a weak oxidizing agent. Okay. So we'll go through an example of each of these cases. So let's suppose we have a strong oxidizing agent and a strong reducing agent. So just an example, this would be, say, copper 2 plus and zinc. Okay, so first we'll find where copper 2 plus is located. Copper 2 plus is somewhere in the middle. It actually appears twice. Since it is, I guess, the upper half of the standard reduction potentials, this is actually a somewhat strong oxidizing agent. It's not the strongest oxidizing agent. The strongest oxidizing agents like fluorine and then disulfate. Hydrogen peroxide is also a very strong oxidizing agent, but copper 2 plus is a relatively strong oxidizing agent. And then we'll look for zinc. Solid zinc is near the bottom, I believe. Yeah, solid zinc is near the bottom. So zinc is a relatively strong reducing agent. So in a case like this, because we have the copper 2 plus is quite a bit higher than the zinc, so copper 2 plus will gain electrons to become copper solid, and zinc solid will want to give up its 2 electrons to become zinc ions. This type of reaction will occur. Redox reaction will occur because you have a strong oxidizing agent wanting to gain electrons. You have a strong reducing agent wanting to give up electrons, and the two of them combined will have a happy reaction. The copper 2 plus will gladly take the 2 electrons that the zinc is giving up to become solid copper, and the zinc will happily give up its 2 electrons to the copper 2 plus to become zinc 2 plus. Okay. Now what will happen here also is that if you look at the copper 2 plus, this has a electric potential of, write it down here, positive 0.34 volts, and then the zinc the zinc oxidation, because it's giving up its electrons. The zinc oxidation has a positive voltage of 0.76 volts. Okay, and remember, it's positive. On your table, it'll say negative 0.76 volts, but that's for the reduction reaction. We're concerned with the oxidation reaction, so we swap the signs. So overall, this reaction has an overall positive voltage of, I think, 1.1 volts. And it's positive. That positive voltage means that this reaction will spontaneously occur, or will occur, because it has a positive voltage. Now, what if the reducing agent is higher than the oxidizing agent? So for example, we have silver, or this example shows silver and chromium 3 plus. If you look for silver, silver is actually pretty high up on the list. So silver is, it's in the upper third of the list. Chromium 3 plus, on the other hand, is quite a bit lower than the silver. So the chromium 3 plus is a weak oxidizing agent. Okay. And if you look for where silver is located, and again, we'll make a note that this is solid silver, not the ionic silver. Solid silver is a pretty weak reducing agent. So weak reducing agent. Okay. What does this mean? Well, if I write the reactions down, so the chromium 3 plus as an oxidizing agent wants to gain 3 electrons to become chromium solid. And this, according to our table, has an overall voltage of negative 0.74 volts. Now the silver has the following reaction. We want to go the reverse because we're given solid silver. So this is the oxidation reaction of silver, and this has a voltage of, normally it'd be plus 0.8, but because we're going in reverse, it's a negative 0.8. So this reaction has a total voltage of negative 1.54 volts. So this negative voltage means that this reaction requires energy to proceed. It's not going to be a spontaneous reaction like the previous one because it has a negative energy. Okay, so this reaction won't occur, at least not naturally. We can force this reaction to occur, which we'll talk about later, but naturally this reaction doesn't occur. Which is great because, as you notice, if solid silver were to react spontaneously to become ionic silver, then our silverware and silver jewelry would just spontaneously dissolve, which is not a good thing because silver jewelry is generally expensive. That's actually just part of the reason why silver jewelry is very expensive, is because it doesn't spontaneously become silver ions. A similar thing can be said about gold. Gold is an even weaker reducing agent than silver, so it makes gold really valuable because it doesn't spontaneously turn into gold ions as easily. Okay. Alright, so now here are 3 examples, 3 pairings, and I want you guys to determine whether the reactions will occur with these 3 pairings. So as with other examples like this, pause the video, consult your tables, and we'll come back to it. Alright, so the first one, we've got Fe2 plus, or not Fe, yeah, Fe2 plus, sorry, Fe2 plus and F2. So F2 is the strongest oxidizing agent on your table. So as long as Fe2 plus is anywhere below F2, then this reaction will occur. And Fe2 plus does show up. It shows up in 2 places, one as a reducing agent and one as an oxidizing agent. Regardless, it shows up as a reducing agent, so this will occur. This will occur. Okay, Fe2 plus is higher than Fe2 plus, and they are on opposite sides. For some of the metal ions like this, some of them will actually appear on both sides of the, some of them will appear as both an oxidizing agent and as a reducing agent, so you have to look carefully. In this case, Fe2 plus is, F2 is higher than Fe2 plus, and this is, I'll make a note here that Fe2 plus as a reducing agent. Not all metal ions appear as both reducing agent and oxidizing agent, but some do. The next one, copper and strontium. These are both the elemental forms, so the solid forms. They're both on the reducing agent side, so this reaction will not occur. This will not occur. The last one, SN2 plus and Pb2 plus. This one, I think you should be able to find SN2 plus as a reducing agent and an oxidizing agent. So this one is, according to our table, SN2 plus is, they're both weak oxidizing agent, and it is also a weak reducing agent. Pb2 plus only appears as an oxidizing agent. Yeah, so Pb2 plus only appears as an oxidizing agent. So even if the tin were to adopt its reducing agent form, it's a weaker reducing agent than the Pb2 plus, so this will not occur. Will not occur. Because again, the SN2 plus as a reducing agent is weaker than the Pb2 plus as an oxidizing agent. Not by much though, but still weak enough that this reaction will not occur. And you can even check using voltages if you're not certain. So like for example, if SN2 plus is, so here's the reaction in our textbook for SN2 plus. This will have a voltage of negative 0.15. Normally be plus, but again we're looking for the reverse. Pb2 plus will have this reaction going to Pb solid, and this reaction has a voltage of negative 0.13. So altogether this has negative voltage, so that means that this reaction will not occur, at least not without some help. Alright, that said, you guys should be able to complete today's assignment then, as follows. If you have any questions, you know how to contact me.